Hi, my name is Justin Swanhart. I'm the creator of WarpSQL. It's a distribution of MySQL 8. It has columnar storage. It's called the Warp storage engine. Warp is actually an acronym for word-aligned relational partitioned. I'm just talking. There. You can see my screen. I hope. Okay. So it's a word-aligned relational partitioned database. So it's a column store, and the columns are also partitioned horizontally. So it's horizontally and vertically partitioned. And it has automatic bitmap indexing. I'm indexing a column right now just by running a query on it. It's taken a while. This is a data set that I haven't tested before, so test it live. I'm going to go real quickly through exactly what Warp looks like on disk. So I've got a data directory here. You can see there's binary logs. The binary logs are created by the storage engine, just like any other storage engine. So you can use replication and whatnot with Warp. Although right now, in the alpha beta version, the alpha features are obviously new features. There are no primary keys, so you have to use batch application for replication if you want it to work well. But it will also work with FlexFuse, obviously. You can see here in the card bench directory, this is the little benchmark that I created for this talk. There is a SDI file that's like the FRM file in MySQL versions 5.7 and earlier. It's the data dictionary file for this table because it doesn't store data dictionary information in the InnoDB data dictionary yet. There's a cardbench.data. So there's a data directory inside the data directory. Are you talking to me, Valerie? Refresh the page in the browser. Oh, okay. So inside this directory, there are partitions. And inside each partition, there are files. So there's a -part.txt, which has information about the actual table. That's like Warp's FRM file. And then there are individual files for each column. And for nullable columns, there are null marker columns as well. So each one of the columns inside the table corresponds to one of those files on disk by ordinal value. So the 0th column, which is ID, is the C0. And you can see there's a C0.idx file there. And if we find dot, see, it's only 271 out of 380 partitions, creating the index for the query I'm running right now. So ideally, by the end of the talk here, that index will be created. So the bitmap indexes are pretty cool. They're created automatically. And of course, I can run queries here while that other query runs. So for example, here, let's run, I'm going to turn off parallel query for now. Parallel query is useful for queries that examine lots of data, but not for those that examine small amounts of data. So, show storage engines, right? Okay, so here you can see here's the Warp engine. And Warp is based on a Lawrence Livermore Berkeley project called FastBit, which is the bitmap indexing and column store implementation that the storage engine wraps around. LS. So, oh yeah. Sorry, I'm a little bit foggy headed. I had on some medication for my bipolar disorder. So we're going to turn off the Warp Rewriter Parallel Query option. So Warp has a rewrite plugin that has that makes parallel queries possible. So I show process list here. You'll see these threads running do sleep. Those are parallel worker threads that are waiting to receive work and run it in the background. This is a preliminary implementation of the parallel query in Warp, but it uses an event, and the event runs in an infinite loop, and then it waits a small amount of time if it doesn't have any work to do. So that's how it does manages parallel work for the parallel query. I practiced typing that one. Okay, so there's the I1 column is a 0 or a 1. So it's a very low cardinality column, and the I-10,000 is a 10,000 cardinality column, and so got 150,000 results in 0.72 seconds. If we change this to 0, the amount of time it takes to return results are going to be proportional to the number of results returned. So that last query there is about as fast as it can go with the amount of data that's in this table. So there's a lot of rows. 15 million. Yeah, I think that's 150 million. I can't really read. I don't have my glasses on. Or it's 1.5 billion. Anyway, there's a lot of rows in that table. And I got those results back really fast. Now, comparatively, I loaded this same data into Column Store. And so when I ran those queries, you can see Column Store took 12.817 seconds and Hot 9.992 seconds. So that's significantly faster than Column Store for getting these needle in a haystack type responses. Warp is really, really great for things like sensor data, where you have a large number of sensors and you want to find anomalies in those sensors or things along those lines, because it can intersect bitmap indexes very quickly. Right, so we could say, or those two. Like I said, this may return a large number of results, so it can take a little while. Okay. Well, while that's going, we're still indexing. Let's go ahead and check on the progress of that again. Any questions so far? Oh, just about done. Oh, and there it is. So that took 20 minutes and 31 seconds. But now when we run the query again, it will use the index, hopefully. There we go, 10 rows. So that's significantly better with the index. And if we say, of course, ID equals 2, we should get about 10 seconds for that query as well. And if we say or I1 equals 1, and I 10,000 equals 0. Okay. So about the same, took a little extra time. But as you can see, it can evaluate complex where clauses, very, very efficiently to return results quickly, once the indexes are created. And like I showed there, that index was automatically created. So now whenever you add data, the index will be maintained when you run queries, and the data will be added to the index, and they'll stay in sync, and you'll be able to query that column very quickly from now on, right? So if you have, say, 1,000 columns, but you only use a few of them in your where clauses, but then someone else comes along and now starts to use some new set of columns, they'll just automatically get indexed. And you can remove the indexes at any time. You can just remove those .idx files with the database shut down, and then start it back up, and you can drop indexes that way. So if you find that you've got a lot of extra indexes that are taking up space, then you can clean them up. There are no there's no data compression right now in Warp. There's only index compression. So the index uses a word-aligned hybrid compression. And the reason the bitmap intersection is so fast is because fastbit doesn't have to decompress the indexes in order to do binary comparisons on them. So we can do ands and ors without decompressing the index, which is pretty cool. So that's pretty much the demo of what it can do. It automatically indexes. It uses bitmap indexes, which I showed here. Or we could, I don't want to use any columns that I haven't indexed because I'll take a while to index. So, and I there. See, very small number of results in a very fast bitmap intersection. So 0.23 seconds for 64 gigabytes of data is in this table right now, right? 64 gigabytes of data. And one of those people that will press Control-R way more times than it's necessary to do what I want to do. So 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So I can't do math right now, not in my head. So that's basically the presentation. I'm going to go ahead and stop sharing now, and well, I'll continue sharing. So it's fully transactional right now. So if it crashes, then any data that was loading will disappear. It supports insert, update, and delete. Internally, though, the storage engine is append only. So new versions of rows are appended to the table, and then an alter table has to be run periodically right now to clean up old rows in the table. I have the SSB, but I haven't run the SSB on Column Store. I've only run it on the Warp on this machine. So I don't have benchmarks on Column Store on the SSB. TPCH is kind of difficult to get running. I could do a dbt3, which is the open source TPCH. But yeah, but generally it's really more for Warp isn't necessarily a column store that's best for analytics at scale for examining large numbers of rows. So it performs well on the SSB compared to a row store. A query will take 30 seconds compared to 30 minutes on InnoDB. But it might be still 15 seconds in Column Store. It might be slightly faster because Column Store does handle large result sets or queries that are based on lots of data retrieval more efficiently than Warp, primarily because Warp is not compressed. Now, one of the things that I want to do is try to compress the Warp data using btree or btrfs compression. Well, yeah, it loads data really fast. It just supports parallel insert. So I use the MySQL shell utility, and you can see here it imported data at 34.25 megabytes per second into the CSV file. So 66.85 gigabytes in 32 minutes. So that's pretty fast as far as loading data goes. Loading into an unindexed InnoDB table loads in about 9 megabytes. So yeah, not bad. And I can make it faster. It's just it does string concatenation internally right now. So it's a little bit slower than it should be. But yeah, it's not bad. Column store, it loaded in, I think I have it in here. Oh, this is the results of the star schema benchmark that I ran. So you can take a quick look here. Count star on 60 million rows is 2 minutes 32 seconds. That's going to be slower than column store for its count stars, just on a bare scan of a table. But like I said, when you get into the other queries, it's quite a bit faster. So the second query here ran in 58 seconds and ran it again, and it ran in 10 seconds. And that's a scale factor 100 on the star schema benchmark. So that's once again about 64 gigabytes of data in the fact table. Second query, first time it ran 5 minutes because it had to create indexes. The next time it ran in 32 seconds. This is the only query. This has a brand between two character strings, and FastBit internally doesn't have a between or a greater than less than implementation for strings. So that has to be punted to the storage engine, and it takes a lot longer to run that particular query. 16 seconds for the next query consistently, and then 5 minutes for the last query, then 39 seconds, 38 seconds, 17 seconds. So it's quite fast on the star schema benchmark, but like I said, I don't have numbers on the SSB on this machine to compare them to for column store. But I will do that and make a blog post because I haven't made a blog post in a while, and I'd love to do one in honor of Valery. Well, adding indexes to InnoDB is not trivial in the least. You can see how well the full text index implementation works. It would be easier to add indexes to, say, PostgreSQL, which has a pluggable index layer. The other thing is that the indexes, FastBit internally is append only. The bitmap indexes are very expensive to update, so they basically have to be appended to. And that would be very difficult to do in an InnoDB implementation, unless, for example, the bitmap index was a circular buffer or something. I mean, it'd be a mess, really, I think, to try to just add it to InnoDB. You can, with the Flex views, which is another one of my open source projects, you can take and make a warp copy of a InnoDB table if you want, and then you can use the bitmap indexes and this the primary key. So whatever columns you want to index with a bitmap index, you make a materialized view with the primary key, and then you can use the bitmap indexes within InnoDB. So I think that provides a good solution that's somewhere in the middle of modifying InnoDB, but still making bitmap indexes available to InnoDB or any other storage engine you use that can produce binary logs. Yes, very bad full text. I have quite a few bugs open on the full text index in InnoDB. Okay, I'm going to go ahead and switch to just text chat.